Guys. We just admit everybody to the class. How you guys doing this morning? Okay, give it just a second. Good. All right. Before we get started on wrapping up chapter 1.3, I wanted to make sure you guys, okay, there we go. I wanted to make sure you guys were able to access your quizzes and your homeworks on our grade portal. So I graded the quizzes and the homework, so you should be able to see what the grade is, okay, on your grade portal. I don't know how it shows up for you. I see a whole list of everybody. But then also on that, you should be able to see like comments that I made. Bear with me, the handwriting on here doesn't look so great because I have to make everything on the screen, like I'm writing on the screen, so it kind of comes out all weird. It's basically how the software, realizes it. But you should be able to see my comments. You should be able to see where I've taken off points or added things up or whatever. So go ahead and take a look at that. If you can't access your quizzes or your homeworks, online, how they are on the grade portal, then let me know, and then we can contact IT and then find out like why that's not being accessed. You should be able to do that. Anyway, so go ahead and take a look at that. If you have questions about how the points were added up or how the grades were calculated or whatever, just send me an email or talk to me in office hours and we can go over that. I can't actually do it during lecture because right, we're all set up for doing lecture stuff and I can't access the grade portal. But if you talk to me in office hours or send me an email, then we can take a look at it. Anyway, don't forget this coming week on Thursday we have another quiz. Remember, we always have quizzes or tests on our Thursdays. So this coming Thursday we have a quiz. It'll be the same kind of format that we had before, where it's available from noon on Thursday till noon on Friday, and you have 30 minutes to take it. It'll be predominantly on chapter 1.3. Okay, and I think maybe we'll see how things go with 1.4. We might be able to throw in a 1.4 question in there as well. Right now, what we have up online is for what's due this week in terms of homework is the remainder of 1.3. So you'll see that posted again. So that's like the rest of 1.3. And then also 1.4 will be due on Thursday, all at midnight. I'm not sure if we're going to be able to, if we have 1.5, probably 1.5 I'll make due next week, but I'll change the due date on that if it's set up right now for this Thursday. Anyway, so let's go ahead and get started. Oh, wait. I don't see any grade for either the homework or the quiz. See here, instructor's still working on grading. All right, thank you for letting me know. I will go check that after class today. It should have been done. It's possible there's something in there that got missed, and I will check. So thank you for letting me know about the grade on Canvas, and I'll check it. So by noon today, maybe if you still can't see any grades by noon today, then let me know, and I'll check it again. So let's go ahead and pick up where we were before. So last week we left off talking about the squeeze theorem. Okay, this is now chapter 1.3 again. Okay, so chapter 1.3, so squeeze theorem, right? So f of x is our function that we're looking at, right? And I've got some value c, right? So my limit, right? My limit of c. So as x approaches c on my function. Now remember, we've been basically looking at functions f of x that are relatively straightforward. We can analyze them algebraically or graphically. We can look at them, but f of x invariably is going to be something pretty complex. And so as x approaches c, I want to be able to describe f of x with a fairly simple function that's a greater than f of x as I approach x equals c, as well as with a function that's less than f of x as x approaches c. Okay, so then basically we say that f of x, our function, is squeezed, it's trapped between this upper and this lower function. U of x and L of x, these are much more simple functions, like they're linear, they're polynomials. F of x is going to be a pretty complex function, all right? So it's going to be really hard to evaluate f of x just on its own merit. So I need another theorem that's going to allow me to say, if my function f of x is bounded on the top and the bottom, on upper bounds and lower bounds, by these functions here, and these functions, u of x and L of x, are approaching the same value as x approaches c, so the function values approach the same limit as x approaches c, then I can conclude, because f of x is bounded by these upper and lower functions, that f of x is also approaching the same limit value as x approaches c. So that's all that our squeeze theorem was talking about. Okay, so we were going to work our way through. That's just a recap of where we were. So we're going to work our way through example 18, which basically says we've got this function x times the sine of 1 over x. And we want to be able to use the squeeze theorem to show that as x approaches 0, my limit approaches 0. So we can't use the product rule, product law, because even though the product law would say the limit of x as x goes to 0 times the limit of sine of 1 over x as x goes to 0, we can't do that because the limit as x goes to 0 of sine of 1 over x doesn't exist. So my product rule is going to bomb out, but I know that I can actually get a limit out of here, but I have to use the squeeze theorem. So we will use squeeze theorem to evaluate. Right, we want to know what this thing is doing. So you can plot this. Now, when I plotted this on my calculator, right, so the first thing I did was I made sure I was in radian mode. If you're going to plot any trig stuff, make sure you're in radian mode, otherwise it comes out like garbage. So I'm in radian mode, so x times the sine of 1 over x is the function I'm trying to do. Now, we're looking as x goes to 0, so my window is actually really small. So I'm looking at minus a quarter to positive a quarter on the x bounds, minus 0.25 to positive 0.25 on the y bound. So I've zeroed in quite a bit, right? And so I graphed it. And so my function, this is my sine of 1 over x, right? And even then, I could probably zoom in even farther if I want to see the behavior as I'm approaching x equals 0, because a quarter actually, even though a quarter is a small number, it's still pretty big in terms of how close we want to get to 0. So you can kind of get a feeling for what this behavior looks like. Okay, so I'm just going to come up with this quick sketch so that I can kind of visualize what's happening. So my quick sketch, right, so as x, here's my x, my y. So my function's kind of going like, I'm going to bound it like this. This is y equals absolute value of x. And then I've got y equals negative absolute value of x. We're going to see why that's important later. It's kind of like I'm taking this y equals x function. It kind of looks like this because my sine function is bounded. It's oscillatory. So my function does stuff like this. Okay, so kind of like whenever you multiply a trig function by some other kind of function, it basically reduces this function here becomes the amplitude. So it's going to modulate the amplitude of sine of 1 over x. Okay, so now we know that the sine of x values are between -1 and +1 for all x values, right? So it's just the oscillatory nature of our sine of x function. Okay, so now what I want to do is I'm going to start building up my f of x. This is my f of x function. I'm going to start building that up. So if I think about the absolute value of my sine of 1 over x, that's going to be less than or equal to 1 for all x values that are not equal to 0. I still have to watch out for my domain restriction here. So now what I'm going to do is I want to build up to this function here. So now what I want to do is I'm going to multiply both sides by my absolute value of x. Okay. Now, by the way, this problem, we're just trying to show you how the squeeze theorem would be used. This problem is more complex than something that you would see on like the homework or the quizzes or the tests. But the squeeze theorem is important because it is something that we're going to use in calculus 2 and so on and so forth. It's going to help us evaluate fairly complex problems. All right. So when I multiply this, basically what's going to happen is I'm going to get absolute value of x sine of 1 over x, which is less than or equal to absolute value of x, right? So all I did was multiply both sides of this equation by the absolute value of x, and I'm going to get this one here. So this one, using the rules of absolute value for here, I can move this around. So it's going to look like this. Minus the absolute value of x is less than or equal to x sine of 1 over x, which is less than or equal to absolute value of x. All right, so we can see that here on the graph. So this, oscillatory function is our x sine of 1 over x, okay? This right here is our absolute value of x, right? So we can see that our x sine of 1 over x is less than our absolute value of x. This is our negative absolute value of x right here. Okay, let's draw these in different colors. So this one here is this function here. This one here is this function here, right? That's my negative. And you can see how my f of x is bounded on the upper. So this is our upper, this is our lower function, right? So this is our lower function, this is our upper function. Okay, so absolute value of x, as x approaches 0, right? So as x approaches 0, what's my absolute value of x function doing, right? So I can evaluate these much more simple functions and then use it to come up with an approximation for my x sine of 1 over x, because that's a pretty complex function, but it's bounded on the top and bounded on the bottom by these more simple functions here. So let's go ahead and take the limit of each side. So I'm going to go the limit as x goes to 0 of negative 1 over x, and that's equal to 0. Okay, and then the limit as x goes to 0 of positive absolute value of x, and that's equal to 0. We can see it on the graph, right? As x is approaching 0, my function is approaching 0. As x is approaching 0, my function is approaching 0. Okay, so now, right, because my upper and lower bound functions are approaching the same value, okay, I don't know what this is doing, but I know it's bounded on either side, top and bottom, by these functions here, which have these as a limit, and therefore, therefore by the squeeze theorem, the limit as x goes to 0 of x sine of 1 over x is equal to 0. Okay, so like I said, this is more of like a proof kind of example-y thing where we're basically taking a complex function and we're bounding it on the upper and the lower ends by more simple functions. We're taking the limits of those more simple functions, showing that those limits are coming to the same value, okay? And because they're coming to the same value, then I can conclude by the squeeze theorem that my more complex function is going to the same value as well. Okay. Hi guys, we good? Okay. So this. So I want to talk about some trig limits. And these, we all get these trig limits by the squeeze theorem. Okay, so by the squeeze theorem, I can say my first one is the limit as theta approaches 0 of the sine of theta all over theta is equal to 1. And the limit as theta approaches 0 of 1 minus the cosine of theta all over theta equals 0. Okay, these are all by the squeeze theorem. We're not showing you, I'm not doing any proofs on these. I'm just giving it to you as is. Okay. My other theorems are cosine of theta is less than or equal to the sine of theta all over theta, which is less than or equal to 1. And we want to specify that theta does not equal to 0 on these cases here. Or minus pi over 2. Pi over 2. So my theta is between minus pi over 2 and pi over 2. Okay, so that's using the squeeze theorem. I'm just giving you these trig limits here. Okay. Everybody else set with writing these? Can I, anybody need another second to write them? I'm reading the chat really quick here. Somebody asked if we submitted all of 1.3 last week, should we resubmit again? Yes, please do. Because last week when I graded 1.3, I only looked at the first handful of problems and I ignored the rest of them. So please resubmit the rest of it. If you are now actually doing 1.3 in its entirety and you want to go back and resubmit part of 1.3 for that first part, please let me know so I know to go back and look at it. Otherwise, I'm not going to look. Okay. So yes, please resubmit it. Okay, so now an important concept is we want to talk about limits at infinity. Okay, so now what we're going to do is as x goes to infinity, we're going to say this means that x is increasing without bound. And when we say minus infinity, right, this means that x is decreasing without bound. Right, and what this means is, say I've got some function, it's doing stuff like this, right? Here's my axes. Okay, this is my function here. I want to be evaluating, but what I'm looking at is as x is heading out to positive infinity, right? I'm looking at, right, if you can imagine, if I could extend my axis as far out as I can possibly go, I'm looking at x is increasing without bound. So as opposed to approaching some finite value, right, what's my function doing here? I have to be more creative and think about what's my function doing kind of in a steady state system. And so now this here, right, I'm looking at, this is x is approaches positive infinity, x is approaching negative infinity. This means x is going this way, minus infinity, x is heading that way, right? So these are my values. They get more and more and more and more and more negative, right? I can extend my axis out as far as I can possibly go, okay? So how we need to evaluate, this is the limit, is going to look like this. So the limit as x goes to infinity of f of x, it's going to equal something, right? Or we say the limit as x goes to negative infinity of our function is going to equal something. We need some tools to help us evaluate this, because this isn't a number that I can just substitute in and take a look at. So I have to be able to think about how am I going to work this? So how we think about limits, evaluating limits at infinity, is the same thought process that we use to evaluate horizontal asymptotes on our function. So we're going to think horizontal asymptotes are horizontal asymptote rules. So you have to go back to whenever you had algebra 2 or pre-calculus, whenever you had your rules about horizontal asymptotes. I'm going to recap them now just so we're on the same page. Okay, so now what this means is when I think about my horizontal asymptotes, I have to be thinking about the ratio of the highest degree terms of my numerator and the denominator. Okay, so I have to look at the ratio of highest degree terms of numerator versus denominator. If you're asking me like, well, wait a minute, we actually don't have, if I just have x squared plus something, you know, plus something all over nothing, right? If that's it, if that's all I'm evaluating it, this is like all over 1, which is the same thing as saying x to the 0. So that's when we say our highest degree terms, we're looking at these terms here, okay? So now what I want to do is I have 3 conditions, right? So the first condition is where I have the same degree term in the numerator and denominator. Okay, so same degree term. So what does that look like? It's going to look something like this. Say, for example, I'm going to go 3x squared plus x plus 2, whatever, all over 4x squared plus, it's a whole function, right? So as x goes out to positive or negative infinity, as x gets really, 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 really big, right? So now I look at my degree terms and I say, this one is 2, this one is 2. They are the same degree term, okay? It's as though those terms cancel out. These other terms are going to become so small in their impact on how I'm evaluating when x gets super, super big. They're just going to drop out. So that's why I only look at the highest degree term. When these degree terms are the same, it's as though they cancel out, and I simply am left with the ratio of their coefficients. which in this case is 3/4. 3/4. Think about it like this. X is a really big number, 10 billion. 3 times 10 billion squared divided by 4 times 10 billion squared. Okay, 10 billion squared over 10 billion squared cancels out, and I'm left with 3 divided by 4. Okay, so same degree term, numerator and denominator is my first case. My second case is that the denominator has a higher degree term than the numerator. Okay, what that's going to look like is, let's say 3x to the squared all over 4x to the 5th. Now there could be a whole polynomial here, right? But I'm only concerned with my highest degree terms. So let's take a look. I've got squared over 5th, right? So my denominator has a higher degree term than my numerator. So now what happens is I've got a really, really big number dividing into a small number. Small divided by really big, okay? That means I've got a really big number in my denominator, which means this thing is approaching 0. Okay. Okay, now my numerator is greater than my denominator. Okay, remember this is for horizontal asymptotes, okay? So this is going to look like 3x to the 5th, so on and so forth, all over 4x squared. Remember the process that we did for evaluating the horizontal asymptote, this becomes a diagonal line, right? So we did polynomial division, and then we worked on the limit of the function, of the fraction that was left over as our remainder. But essentially what happens when I'm dealing with my limits now, okay, this thing, even with my numerator over my denominator, I've got a really big number divided by a smaller number, this thing heads off to infinity, right? It's unbounded. Okay. So we think about our horizontal asymptotes. Okay, so that's our horizontal asymptote. Let's take this now and we're going to apply it to limits and think about how we're going to approach our limits. You guys will have this here before I move the page. Okay, right, I'm going to move this down. Okay, so now applying the rules to our limits. So we're going to apply it to our limits. Okay, so now I'm going to say for all n greater than 0, n's a number. Okay, so this is going to be the limit as x goes to positive infinity. I have to put the positive, but I'll say as x goes to positive infinity, x to the n. Okay, so you think about this. I've got a parabola, x squared, n is equal to 2, x squared. As x goes to infinity, this function gets bigger and bigger and bigger and bigger, but I've got nothing limiting this. This thing goes off to infinity. Okay. The limit as x goes to negative infinity, I'm sorry, we'll do negative infinity in a minute. As x goes to positive infinity, x to the minus n. Okay, this is going to be the same thing as the limit as x goes to positive infinity of 1 over x, right? Because the negative says you need to be on the other side of that dividing line, right? So I have a small number divided by a big number. This thing goes to 0. Okay. I'm applying these horizontal asymptote rules, but I'm just summarizing them for our limits here. Okay, so now if n is a whole number, fractional numbers mean I have to, kind of think about it in more detail because it's like a radical, right? I'm taking a root. So limit as x goes to negative infinity, x to the n. Okay, so now I'm heading off in that negative direction where x is getting smaller and smaller and smaller without bound. So what this is going to be equal to is, this is going to be positive infinity if n is even. If you can't remember, n being even is like x squared, x to the 4th. We're talking about parabola-shaped functions, okay? So if n is even, right, and I'm heading out towards negative infinity, I'm still going off to positive infinity, right? If n is odd, okay, I'm dealing with, like, say, x cubed. Think about in your mind x cubed. If I'm heading out to negative values, my x cubed is heading down to minus infinity if n is odd. Reduce in your mind to more simple functions so that you can remember like what these things look like. Or I also want to say the limit as x goes to negative infinity of x to the minus n, right? Remember, this is 1 over x to the n, because we need to kind of think in our mind what that's going to mean. This thing is going to be equal to 0. I think this is minus infinity. Yeah, okay. Yeah, so we're still going to be heading down to 0, because it's going to be getting really big. Okay. Now, what we want to do is, let's take a look at some of our examples here. Actually, I think this is, yeah, that's fine. Okay. So now let's take a look at our examples. So we're going to go through, I tell you what the, oops, sorry, what the numerator and denominator. So there's a couple typos on here, which we'll fix as we get down, because this won't be true. So as we get down to C and D, bear in mind that there are typos. So this means our numerator degree term is the same as our denominator degree term, right? So my x to the fourth, x to the fourth. Okay, so I'm telling you ahead of time what conditions we're taking a look at, okay? So as x goes out to infinity, 3x to the fourth, so on and so forth, divided by 7x to the fourth. Remember, this is the same degree term. We're reducing it down essentially to the limit as x goes to infinity of 3x to the fourth all over 7x to the fourth. Because these other terms drop off, they become so small in comparison to what this is doing. The x to the fourths cancel out, okay, and I'm left with simply the ratio of my coefficients, because the degree terms in the numerator and denominator are the same. Okay. Part B, let's take a look. I've got my numerator is less than my denominator degree term, okay? So basically, because the numerator is less than that, what I'm dealing with here, functionally speaking, is how I want to think about it. As x goes to positive infinity, I'm dealing with 3. Like, I can kind of cancel these out. 3 all over 7x, okay? So the 3/7 doesn't matter anymore, right? 1 over x, as x goes to infinity, small number divided by super big number, this thing heads off to 0. Okay, C, so there's a typo here, so let me show you, let me write this down. Typo here. So this should be instead of x to the fourth, this should be x to the third. So this is 7x cubed minus 4 in the denominator. Okay, and then here I'm heading towards x is heading to minus infinity. Just so we can see these different conditions. Same thing here. This is heading to x is minus infinity. Okay. So now my numerator, my numerator degree term and my denominator degree term, okay, is going to be odd. So 8 minus 3 is equal to 5. That's an odd number. Okay, so now what happens is, right, I'm functionally looking at this is equal to 3/7, the limit of x to the fifth. Okay, but I'm heading, it's going to negative infinity, right? So I'm heading to negative infinity, which means this is heading to minus infinity here. Okay, as x gets smaller, this is odd. I'm heading to minus infinity. It's still unbounded. Okay, my limit isn't going to exist because it's unbounded. Okay, here, right, we're looking at 7 to 3. 7 minus 3 is 4. That's even. Okay, so we're looking at, this is 3/7, the limit goes to negative infinity of x to the fourth. Functionally speaking, that's what we're dealing with, which is going to positive infinity. So, but note, these two limits don't exist because they're unbounded. Okay, but just so that you know, you have an idea about, as x is going out to minus infinity, what is our function doing? Where is it heading? Okay. So how we want to think about our limits. Okay. So, last topic in chapter 1.3 is what we call an intermediate value theorem. Intermediate value theorem is a really important concept, IVT, how we can talk about that. So let me write it out in math. I'll draw a picture to help explain it a little bit. So the intermediate value theorem says if our function f of x is continuous on some closed interval, we're going to write a to b. Okay, so we know maybe the function's doing something wherever, but wherever I'm focusing at from a to b, my function is continuous along a to b. And I want to say if I evaluate the function at a, that's not going to be the same value as if I evaluate the function at b. Okay. Okay. All right. Then what happens is there's a value, a unique value, okay, between f of a and f of b, which we'll call m, between f of a and f of b, okay, that exists at least once, okay. This is x equals c, right, which is along this interval of a to b. This is a lot of words. I'm going to draw a picture so it'll make sense. Okay, and we're going to say that f of c equals our m. So let's draw a picture so we can see what I'm actually talking about. So I've got my axis, x and y. So here's my interval a to b. Okay, and I've got my function, you know, it's doing something. I'm going to draw out my f of x. Okay, so let's take a look. So I've got my, this value here is my function evaluated at a. Here's my function evaluated at b. Okay, these are the values, right? These are my x value, my y value, my x value, my y value. Okay, now what we're saying is between that interval a to b, there exists some value c. Okay, this is here, and this is equal to, we're going to say m equals f of c. Okay, so now what happens is I know my function f of x, and I can calculate a and b, right? I know a and b is my interval that I'm looking at, right? And I want to know, you know, c is some value between a and b, right? That's what we mean. It's within this interval, a to b. Now, that means, right, because it's continuous, that means that I've got some value of the function f of b, I've got some value of the function f of a. I know my function has to have some value at c, f of c, okay? So my intermediate value theorem says, if I know what f of a and f of b are, then I know that f of c has to be between them somehow, okay? It seems like, this is pretty obvious. I can just plug it into my calculator and get this. This is the algorithm that your calculator uses to calculate what is f of c, right? So I want to be able to kind of localize, right, what is this value here and what is this value here, okay, f of c. But I'm going to use my knowledge of f of a and f of b to help me basically narrow down that window. Okay, so we're using the intermediate value theorem to do that. It helps to take a look at some examples so that we can see what this thing does. So let's take a look at example 20. We're going to use our intermediate value theorem to talk about the sine of x equals 0.3. Okay, so we know that the sine of x, we want to say that it has at least one solution. Okay, so we know the sine of x oscillates between, you know, positive and negative 1. Right, and so, you know, 0.3 is the value that I'm looking at. So I want to know at what x value is going to give me the sine of x is equal to 0.3. So I'm going to apply my intermediate value theorem. And I can do this because the sine of x is continuous. It's continuous for all real numbers, right? So I'm going to choose an interval of x values that I think is likely to contain sine of x will be equal to 0.3, that I think likely to contain, like the sine of x is equal to 0.3, right? So I know, right, just from my basic trig that the sine of 0 is equal to 0. And I know that the sine of pi over 2 is equal to 1. So I go on my graph. So the sine of 0 is the sine of 1. So I'm looking at, right, my x values, my interval is going to go from 0 to pi over 2. This is my interval. my interval of x values, right? So now look at this, my interval of y values, my y values, between 0 and 1, 0.3 exists. Y values, 0.3 is between 0 and 1. So I know that my x value that's going to generate sine of x equals 0.3, that x value has to be between 0 and pi over 2. So value of x that will give sine of x equals 0.3 will be in between 0 and 1. It'll be along that interval 0 to 1. Okay. This method, example 21, we're going to actually talk about how we narrowed that window down. 0 to pi, I'm sorry, it should be pi over 2. Sorry about that. 0 to pi over 2. So 0 to pi over 2 is actually a pretty broad window. So what we would want to do is start narrowing down that window and say, is 0.3 in this interval, is 0.3 in this interval, is 0.3 in this interval. We're going to do that here in this example, okay? And the reason we're talking about this is because it's an algorithm that our calculators use, that our computers use to help us figure out what are these values of sine. Otherwise, I need to like plug in, you know, like a whole lookup table for sine, and I want to do that on my calculator. All right, so let's just write down a little note. Note, we can use our intermediate value theorem to help us find the zeros of a function. The zeros of a function are important, right? That's where the function crosses the x-axis. I want to know where's my function equal to 0, right? So we're going to talk about how we're going to do that in example 21. Okay. So we're going to use what's called the bisection method. And I'm going to talk about the bisection method as we're doing it. It's an algorithm often that actually gets used in computer science too to help look up things. Okay, so now I can plot this on my calculator just so I have a visual, right? So this thing goes, and I'm going on the interval 0 to 2. So it's going to look something like this. Here's 0. Okay, so this is my function here, f of x. Right, so it has some kind of, you know, by my graph, I can tell that it has a 0 crossing, okay? But now I want to be able to locate maybe that interval where that 0 crossing is happening. So I'm going to use my calculator to come up with some values. So I'm going to look at my endpoints on my interval. So my endpoint f of 0, I plug that into here, and I'm going to get out f of 0 is equal to 1, which is a positive number, right? If I plug in f of 2, that's my other boundary point, I plug that into here, you know, make sure you're in radian mode. That's approximately equal to minus 0.786. That's a negative number. Sorry, my daughter has her first day of online classes today, so she's trying to locate all of her classes on her Zoom links for it. So I gotta go check on her when our class is done. That's the background noise you can hear is her panicking trying to find that. Anyway, so f of 0 equals 1, f of 2 equals a negative number, right? So because our sign changed, we have a sign, change. Sign is in positive to negative, right? Positive to negative between our x values 0 to 2. That means that our function has a 0 within this interval. Means our function has a 0 in the interval 0 to 2. But 0 to 2 is a pretty broad interval. So how can we figure out, let's narrow down. So to narrow down the interval, right, from 0 to 2, I want to narrow it down. I'm going to bisect that interval. Bisect our interval, right? So by bisecting it, I'm going to cut it into half, right? So I'm going to cut it into 2 pieces. So I'm going to go from 0 to 1 and from 1 to 2. I'm cutting my interval from 0 to 2 in half. Okay. Okay, so I need to check my boundary value. So this is my first bit. So I cut it into half and then check boundaries, values for a sign change and see where the sign change happens within each interval. One of these intervals, and then ask ourselves the question, which interval, could be both if our function does multiple things, which interval has a sign change? Okay, so let's do it. So I'm going to plug this in. So I'm going to go f of 0, which we already knew from before is equal to 1. That's positive. And then f of 1, I plugged that into my calculator. F of 1 is approximately equal to minus 0.203. Oh, so that's a negative number. So I have a sign change between 0 and 1. Let's just check here. If I go f of 1, that's a negative number. F of 2 from before was also a negative number, right? We had that from before. So there's no sign change. 1 to 2, there's no sign change. But from 0 to 1, there is a sign change. Okay. My next step is repeat, right? So then my next step is repeat steps, which means what I'm going to do now is I'm going to cut my interval 0 to 1. I'm looking for the 0, so I'm not going to worry about my interval from 1 to 2 anymore. I'm going to cut this one down. So I'm going to go 0 to 1/2 and 1/2 to 1. And I'm going to check to see which interval has the sign change in it. Okay, one of these intervals is going to have the sign change. And then I'm going to cut that in half. I'm going to keep cutting those intervals down smaller and smaller and smaller by half. Half is an easy method to do. Cut it into half each time. Find out where that sign change is happening, right? Going to positive to negative. And then ultimately that interval that I'm checking is going to get so small, right, that I'm functionally looking at where x is equal to a value that's going to tell me where my 0 is happening. Okay, so that interval of x values gets so small that I can functionally say, right, that I've hit where the 0 is. So keep cutting interval half to get sign change. You can stop when interval is small enough. Okay. The whole idea of small enough, we're going to talk a lot about in calculus too. Okay, that's something that would come down from like design specifications. How precise you want your x value to be. So don't sweat it right now. I'm just going to leave it kind of loose in terms of saying it's just small enough. Okay, so when the interval is small enough, then we can say, right, our 0 is at x equals some value. Okay, so we've cut our interval down so small. X is between such a small boundary value that I can basically say x is equal to this. That's where our 0 is. Small enough, that's a parameter that gets set outside of the functions here. Like some design team says, okay, we want this to have an error of some value. I want my my x to be, out to how many significant digits, right? That's all going to depend on how we're designing our system. Don't sweat it. Right, we'll tell you how far out to go, okay? But that's called our intermediate value theorem, and we're using the bisection method to do that, okay? All right, what I'd like to do is, that's the end of chapter 1.3, okay, guys? I will scan in the 1.3 lecture examples and post them onto our website later today. I teach 2 sections of this class, and our sections are a little bit off sync. We're actually quite ahead of the other section, and I want to get you guys back on the same schedule. So I think what I'm going to do is the other section, we're going to start 1.4 tomorrow. So I think I'm going to, instead of jumping ahead and starting 1.4, I'm not going to start 1.4 right now. I want to get you guys back on the same concept, the same schedule. So let's talk about homework for 1.3. If you guys have questions about homework for 1.3, I'll be happy to answer those questions. I think somebody had a question on question 47 last time, which I'm happy to talk about now. We have actually the skills. So let's talk about homework chapter 1.3. Okay. Just if you have any questions, I'll do question 47. And then if you guys have other questions about it, you can ask me, and then we can go over those problems, and then we can end class so that our classes will now get back into sync with each other. So this one was the limit as t goes to 2. This is 1 over t minus 1 over 2 all over t minus 2. I think this was the problem that we were looking at. Now, if we do direct substitution on here, I'm going to get a divide by 0 problem. So what I want to do is start cleaning things up, right? So if I maybe can find a common denominator, bring the numerator together, and then cancel things out. So I've got to start thinking about maybe cleaning up this fraction here. So I'll do some algebra offline here. So my algebra offline is going to look like my common denominator is going to be 2 over 2 times 1 over t minus 1 over 2 times t over t. So then, and this is all over t minus 2. So this looks like basically when I bring it together, I'm going to get 2 minus t all over 2t all over t minus 2. Okay, this is all over 1, right? Because I want to put it into a fraction over fraction form. So I'm going to get 1 over t minus 2. So I multiply top and bottom by the reciprocal of the denominator. So let's bring it back into our limit again, t minus 2. So I'm looking at 2 minus t all over 2t, t minus 2. I saw on the quizzes and on some of the homeworks that you guys multiplied through, and then you got some kind of quadratic, and then you didn't know what to do because you couldn't cancel anything out. Often you just maybe want to leave things in terms of factors, okay? And then that way you're going to be able to see this is 2 minus t, this is t minus 2, but if I factor out a negative here, I'll be able to cancel out these terms. So I'm going to do that. So the limit as t goes to 2, I'm going to factor out a negative 1 here. That becomes t minus 2, right? Which is going to allow me to pretend I'm going to remove this discontinuity here. Goes to 2, so I'm going to get minus, that's a 2, 1 all over 2t. Okay, so now, right, now I can just do substitution. So I'm going to get minus 1 all over 2 times 2, which is equal to minus 1/4. Okay, so that's where my function, that's how I'm going to evaluate this limit here. I can't do substitution directly at the beginning, right, because I'll get a divide by 0 problem, but I can start working things through, just doing a bunch of algebra to combine things, okay, and then I can pretend, right, I'm just rearranging my function so that I can evaluate the limit, but the function still has a discontinuity here at t equals 2, but the limit is approaching minus 1/4. Okay. I think that was a question somebody asked last week, but it wasn't due, 47 wasn't due last week, so now we have the skills to be able to answer it. Okay. I'm looking at the chat. If you guys have any questions on homework for 1.3, I'd be happy to answer them now, or you can come to office hours and we can talk about it. 46, okay, so let's take a look at 46. 46 is going to be similar to this one too, some algebra that we need to reevaluate. So the limit as x goes to 1, I've got 1 over radical x minus 1 all over x minus 1. Okay, so the first thing I'm going to do is I'm going to think common denominator on here. So I need to multiply top and bottom by radical x. Okay, so I can start bringing this together. Goes to 1. This is going to look like a 1 minus radical x all over radical x minus 1. Okay, so this is a case where I need to be able to think about how I want to approach it. So this one here, right, I can't combine anymore because I've got these radicals. So I can multiply by the conjugate. Right, so my conjugate, so if the function is 1 minus radical x, the conjugate is going to be 1 plus radical x, right? So if I'm just multiplying top and bottom by the conjugate here, so this is going to be 1 plus radical x, 1 plus radical x, right? I'm multiplying top and bottom by the same thing, so I'm actually just multiplying by 1. So all I'm doing is rearranging, but remember 1 minus radical x, 1 plus radical x, we're going to FOIL it out, right? So it's going to give me the first outer positive radical x, inner minus radical x, and then last, this is going to be negative, right? Radical x times radical x is just x, and this on the denominator, I'm just going to leave like that. Okay, so these terms cancel, and what I'm left with is now bring back the limit. Right, so what I'm left with now is let's see, 1 minus x, right, because the radicals canceled, all over radical x times 1 plus radical x, and that's all over this one, x minus 1, and that's over 1. It's a fraction, right? So I'm going to multiply by its reciprocal, x minus 1. So I need to factor out a negative here. There's a lot of algebra in this one, right? So if I factor out a negative, then I'm going to get negative 1 times x minus 1 all over. Let's write it like this. X minus 1 times radical x times 1 plus radical x. Okay, so now we can pretend, right, that we're going to cancel out these repeated factors. Just when I've got the negative, don't forget your negative, all over radical x times 1 plus radical x. I'm headed to 1, right, which means now I can just do substitution, okay, which is going to be minus 1 numerator. This is going to be radical 1 times 1 plus radical 1, which is equal to minus 1 in the top. 1 plus 1, that's 2. This thing heads to minus 1/2. Okay, it's a lot of algebra. But this one relies on our conjugate in order to simplify. Okay. 35. Okay, I'll give you guys a chance to. Okay, yeah, this is a piecewise function. You guys, I'll give you a second to finish writing that down, and then I'll bring up 35. Okay. Are you guys all set with 46? All right, I'm going to move the page. This one is question 35. This is a piecewise function. So I've got the price. Let's write it down. So this is 0.8 for when x is less than 500, less than or equal to 500. 0.72 for when x is between 501 and 1,000. And then 0.65 for when x is greater than 1,000. Okay, so oh, and we were told that the cost is equal to x times the price. Okay, so quantity times price. All right, so now let's graph out our cost function. This is c of x. Cost is a function of x. So my I'm going to write out 500 and 1,000. That's where things are changing, right? So my function goes like this, x times the price. So I've got the slope. It's just a linear function. So up until about here. So this thing goes here. There's a solid line. And then this is, I'm going to call this, this is 501, right? Because it kind of starts right there. So 501. And did I write that down right? I have dot right there. And then this is also a straight linear function until about 1,000, until here. Slightly different slope. And then greater than, this thing goes like that. Okay, so there's our piecewise function. And I did this as a 501, because otherwise at 500, it would be an open circle here. So if I did it, I'd have an open circle, but I tried to really exaggerate the space. In reality, you wouldn't see such a big space here when we're graphing it out like that. Here's our cost. Here's our x value or quantity. Okay, so now what we're asked is the limit as x approaches 1,000 from the left-hand side. From the left-hand side, I'm looking at 0.72 x, okay, which is going to equal to 720. Okay, so I'm approaching it from the left-hand side. I'm going to approach it right here. Okay, and now the limit as x approaches 1,000 from the right-hand side is 0.65 times x, which is 6. I'm approaching it right here. Okay. I think I drew those. I think this should have been down here. All right. Okay, and I think that that was it. That's all I have in my notes in terms of like what our left and our right hand limits are. I think I don't have the question in front of me. I just have my solution. Okay. I think this is probably supposed to be down here, and then it goes up. There. Okay. If you guys want to talk about any other questions, you know, for chapter 1.3 homework and stuff, you're free to ask me in office hours, and then we can go over it and talk about it. But the rest of 1.3 will be due on Thursday. Okay, you can just resubmit the whole thing. It's fine. I'll take a look at stuff that's there. If, like I said, if you're doing it for the first time, submit the whole thing on Thursday, and then if you want, submit like the first few problems, or if you have it in one PDF, just submit it into the old homework. But send me an email to know so that I know to look at the old problems, and I'll go take a look at the Canvas page and make sure everything is okay. Okay, guys. Have a great day.
Thank you.
Bye.
Thank you.
Take it easy.
Thank you.
Bye.
Yeah.